All right. Okay. So it looks like we still have a little bit of an audience. Most of the summer students have left, although two are here still. Um, yeah. So how to begin? So this lecture is the last lecture of the course, and it's basically something not too involved. It's simply a send off of where kind of I think fMRI is and where it's going in some regard. Um, uh, and first, I'd just like to go over the course, not in detail at all, but just to mention that we've had 41 lectures, and we tried to fill out the topics to be comprehensive and to hit upon all the potential opportunities and expertise here at the NIH, and also to hit upon the areas in fMRI in particular, and as well as other neuroimaging modalities that are relevant and cutting edge. We might actually do things differently next year. We might have a few less lectures, and then rather than covering all the basics or an attempt to cover all the basics, we'll try to maybe make them focus just on like an issue per week or a couple of issues per week to just hit upon. And then hit upon that not only at a high level, but also maybe get more of the nuts and bolts of the issue. Whereas I think a lot of people here are not just in a position of learning, but they also are doing it and they just want to know what to do and know how to do it best. And so we might, I'm just already thinking that we might redo that a little bit. We've had this course now for years, and so it's maybe a good idea to sort of reconsider that. So, all right, so now into the lecture. So fMRI is about 26 years old now since the first results. And in fact, it's almost exactly, as far as my own personal experience with fMRI, my first successful results were September 16th in 1991. And so that was almost exactly 26 years ago. So how have things improved? So this lecture is going to be a little bit different in the sense that I'm not covering, it's not going to be long. It's also not going to have any figures or diagrams or results or anything. It's just going to be basically just getting right to the point of what I think has improved, what hasn't improved, where we're going, and things that might change everything as well to always be aware of. So what has improved? So first of all, the technology is steadily improving. Computers are getting faster. The imaging technology has been improving in a very stable way. It's more sophisticated, it's more powerful, it's more stable. That results in better image quality, of course, higher resolution, less signal dropout, better temporal stability as well. And a lot of the reasons why things have been steadily improving hasn't been, and this is sort of a theme I come back to a lot with my talks, and I'll come back to here, is that we're sort of riding on the back of the MR industry. And because that keeps on growing, that has so much of a customer base, that they're highly motivated to keep things going, improving the scanners, improving the field strengths, and we're just sort of riding along. They're not really paying much attention to fMRI. And one of my points later on is that once they do start paying attention to fMRI, if it becomes more clinically relevant and actually has a market, then we'll probably see more rapid improvements in functional MRI technology. Because right now, if we write a pulse sequence, for instance, we can distribute it, but it has to become a product in some way for it to get universal acceptance. Okay, so fMRI is easier to implement. In the old days, we had to do a lot more things, enter in like individual variables by hand. We had to a lot more sort of low-level programming to make it run. It was a little bit more clunky. Now things are very smooth, much more smooth. Well, that's weird. I'm going out of order for some reason. Maybe I didn't order it right. So the artifacts in fMRI time series are more easily identified and removed. This has been an ongoing struggle ever since the very beginning. At first, we didn't even realize that they were artifacts. Now we realize that they're potentially artifacts like breathing, motion, heart rate, and we're still trying to remove them, but we've gone a long ways in sort of automating that. All these brand new processing methods that you've heard about in the last several months, multivariate decoding, encoding, pattern effect mapping, machine learning, cross-subject correlation, dynamic resting state connectivity. They've all not only have pushed along sort of the methodology for applications, but they've opened up completely new directions as far as how to look at the data and how to actually pull out information from it. And also there's more standardization in the acquisition, the processing, and display. So if you know, I mean, there is some differences among vendors, but there's still, if something's a certain resolution, you can be sure that it's pretty close to that resolution in another vendor, another scanner. Pulse sequences have been sophisticated, improved such that slice profiles are similar. So the image quality has sort of generally become similar and more standardized. Okay. Number of groups of working with fMRI have all increased. That's a great thing as well. It keeps on increasing. It may have plateaued a few years ago in some regard because OHBM, for instance, sort of a measure of the number of people doing neuroimaging has sort of plateaued around 3,000 or so, maybe about 8 years ago. So maybe that has plateaued. Underlying neural correlates of fMRI are better understood. So we still don't understand everything, but people have done single unit recordings, calcium channel imaging, that's simultaneous optogenetics for stimulating areas and showing that there's an actual bold effect in those neurons that they're stimulating. So we have a better sense that what we're looking at not only is close to neural activity, but the degree of activation as it's modulated is modulated by the degree of activity. We still don't know, for instance, though, is it the same thing looking at a voxel if you have many neurons firing a little bit versus a few neurons firing a lot? We don't know that question, a very basic question. We still can't differentiate inhibition from excitation. So I'll get into that as well. But we have come along enough that even looking at resting state, we know that these fluctuations, a good half of the energy is neural activity, spontaneous neural activity. So research applications have increased. So the technique still is growing in that regard. Resting state has exploded. Large pooled data sets. A big aspect that's recently been happening is you have these massive data sets that people are feeding into that we're starting to beginning to do meta-analysis on, or trying to derive biomarkers by looking at individual differences among those data sets. So that's just starting, and it holds a lot of promise as far as that's concerned. In fact, I would actually even argue that that's probably one of the futures of fMRI, is to sort of feed into these data sets and have people keep on reanalyzing this data in ways that pull out even more information. Because I think my feeling is that when we collect data, there's so much information there that we really only scratch the surface when we do our preliminary analysis of mapping where areas occur or whatnot. So there's more to be had there. Individual assessment, as it's linked to large databases and smaller studies, is also growing. It's sort of, it's interesting even mentioning this, because I remember in my last BSc, not the most recent, not the one for the core, but our previous one for the section, we were talking about individual assessment, and even then it didn't really catch on. Even Camille Ugerbil, obviously he's been pioneering a lot of things. He asked the question, so you can do individuals. You tap the fingers and you see the activation. We've been able to know, we've known that for 25 years. But in fact, that's very different than this individual assessment. So what we would like to do is have people tap their fingers and then be able to tell if they're left-handed or right-handed, for instance. There's a huge difference in yes, we can see signal, but can we derive some information about that subject from that signal? And that's a much harder problem that I think a lot of fMRI is going towards. So we've made a huge amount of progress like that, like I mentioned. So 5 years ago, no one was thinking about that. And now I think that most of the field sort of senses that this is a cool thing to start doing. So the highest resolution and the fastest speed have all increased. Of course, the upper limits have increased. Not that much. I would say that the highest functional resolution has almost peaked out in about 2000, 2008 or so, when we had an orientation column paper by Yakub, actually showing that that's the upper limit in terms of the hemodynamic response. However, we're also doing layer dependencies and things like that, but still the upper limit maybe has peaked as far as that's concerned, maybe sub-millimeter, just barely below a millimeter resolution. We can certainly go much faster, though. We can collect very thin, many, many, many more slices per TR. That just occurred a few years ago with parallel imaging. So the standard resolution has increased as well. What we typically do when we throw a person in a scanner and do your average study, that's gone up a little bit. In the beginning, it was about 3.2 millimeters cubed, 3.5 millimeters cubed. Now it's about 2.5. It's improved, but it hasn't improved a lot. And there's probably good reasons for that. We're still somewhat signal to noise limited. And also, if a lot of studies still do multi-subject averaging, it doesn't do much good to collect at higher resolution anyway. So most people are still using less resolution than they could. And of course, there's more high field scanners. There's about, I would say, 60 in the world today right now at 7 Teslas. Hopefully, a few more will grow. I used to be more optimistic about higher field strength scanners, but I actually think that we've reached a point of diminishing returns. At 7 Tesla, right now, it's sort of a sweet spot. Until we have some substantially new technology, and until there's clear evidence that you get huge gains at much higher field strengths, I think that will sort of stall out. My feeling, though, is that, for instance, there's even a study that was published a while ago that seemed to suggest that BOLD kind of topped out at 11 Tesla as well. And the reason for that is that it's driven by magnetic field gradients around vessels. And so, but as you get to a larger and larger field, these gradients get larger and they spread out and they start overlapping. And so eventually, because of the distance and between vessels and the size of the amount of susceptibility, you might have overlapping of the fields, and there's not that peak and trough as much, and so you don't gain as much contrast in that regard. So that's a thought that might happen around 11 Tesla. So you might start getting diminishing returns, and of course you have diminishing returns in terms of SAR, signal dropout, and just general stability. And also there's more multimodal integration. So that's always been going on. I think the first simultaneous EEG and fMRI study was done in 1995 or 6, but once again, it's easier to do it now. The technology's improved. There's companies that make these systems. So that's all improved. And it's interesting because the technology's there, but there really does seem, with a lot of the applications of these techniques, a bottleneck in the users. The people are not necessarily embracing them as much as they could. So we're just waiting on, working it through to actually have applications. Okay, so what has not improved? I kind of talked about a little bit what has not improved in that slide, but what hasn't improved? So we're still struggling with motion and breathing, and that's always been a problem. At least we recognize it more as a problem now. Subjects still move. We still haven't figured out exactly how to get around this. No matter what algorithms we use for post-processing, no matter how much we constrain subjects, we still have breathing effects as well. So breathing manifests itself in several ways. You have the B0 changes that occur with each breath, and then you have the subtle changes in end-tidal CO2 that cause subtle changes in blood flow as your breathing depth varies over time. So that's still a huge factor, and the problem is that later contrast overlaps exactly with the resting state fluctuation frequencies, about 0.1 hertz. So, or even less. So that's actually something that we're still struggling with. Still struggling with the hemodynamic response function. And so many times, though, I think a lot of people, right from the beginning, they tried to just ignore it. So for instance, people early on tried to do causality right from just looking at the responses, either applying Granger causality or just looking at the responses, saying, oh, look, the signal went up just a little bit ahead of time in the premotor versus the motor cortex. Therefore, the premotor influences the motor cortex. And of course, we've learned that you can't do that because all over the brain, you have different latencies of the hemodynamic response. And until we get a good, robust method for calibrating that on an individual subject basis, we really can't just pretend the hemodynamic responses are not there, unless we also modulate the task and get relative timings and things like that. But that said, we're still struggling with that. And also, the same goes for magnitude. You might have a large, bold response in some area, but that's typically because you happen to be over a large vessel, or it's directly proportional to the blood volume in a voxel. So we still haven't gotten around that problem as well. Certainly, if you parametrically vary the task, you'll see the signal go up. That's more proportional to neural activity. You can imagine some areas don't go up at all, some areas go up. That's more of a neural effect that you can get at. But if you're just looking at the magnitude, largest activations are vessels, and you have to sort of interpret around that. The temporal signal to noise is still limited by physiologic fluctuations. So this is something that is almost kind of embarrassing, because I remember talking about this back in 95. I remember mentioning that I wanted to do this as one of my projects as a postdoc, is get rid of all physiologic fluctuations. So if you remember that curve that we show, that's basically, if you look at the image signal to noise versus the image signal to noise on the x-axis, the temporal signal to noise on the y-axis. If you have a bottle of water, that's just a straight line. But if you have a brain, it goes up and then it plateaus out at about 120 to 1. And even though we can do filtering and if we try to regress out the physiologic fluctuations, we can try everything. We still don't understand the fluctuations enough to make that plateauing out go up. And if we could do that, 50% of the energy at least is physiologic fluctuations that we don't care about. If we could somehow move that such that the image signal to noise is a reflection of the temporal signal noise, that would be a breakthrough, because then we could have time series. We wouldn't have to go to high field strength. We could have time series with the signal to noise, a temporal signal to noise of 1,000 to 1, because that's typically what we can get the images to be. So, but right now they're 120 to 1. The temporal signal noise is 120 to 1 about. And so we're stuck with that for now. fMRI is still not used clinically. Some would argue with that. It might be used a little bit in pre-surgical mapping, but it might be used maybe for replacing the WADA test a little bit, maybe a few other things, but it's all extremely tenuous. And the problem really is that there's so much variability that we don't understand in fMRI, and there's so many steps in the processing that there's variability in the signal, there's variability across subjects, that it hasn't yet settled in. We haven't figured out a way to find that killer application that we can put a subject in the scanners. As I always like to mention, it's one thing doing population studies where you say, oh, there's a difference in the population, 2 Gaussians, you can easily find a difference. But it's another problem altogether if you take an individual subjects and figure out which distribution they actually belong to. So, and that's the problem we're up against right now for us to apply it clinically. Spatial resolution of fMRI has reached a theoretical limit due to hemodynamics. That hasn't improved. So that's sort of plateaued out around 2008. And it's still good. It's still only a very, very, very few studies doing work at that resolution, but that's pretty much it. We're limited to orientation columns or layers, which is small, which is sub-millimeter, but we can't go much better than that, just because the hemodynamic control is not any finer than that, which actually might be a good thing, might be indicative that the neuronal populations are somewhat homogeneous within that size of an area, maybe. Okay. All right. Okay. So as I mentioned before, vendors haven't put many resources into fMRI. That's still a problem. That hasn't improved. Maybe they've done a little bit more work, and maybe we've benefited from it, but they really haven't paid attention to fMRI. Scanners are still loud and confining. And until there's a complete breakthrough in technology, at least for the confining part, that won't change. The loudness, there's ways of doing active noise cancellation, potting gradients, designing pulse sequences that don't drive them as hard. There are ways of making things silent in that regard. And also, of course, you can do, with active noise cancellation, that technology is still improving as well. It's extremely expensive still. It still costs, on average, clinically, $1,000 a scan, research about $500 a scan for an hour. So that's still prohibitive. That will only go down as fMRI or MRI becomes more distributed and more sold. The market gets bigger. So like I mentioned, we're still using 2.5 millimeter voxels for most studies, which is good, but not something that we could all be going higher, but maybe it's not the best idea to go necessarily higher for all things. Another thing too, this is sort of more scientifically, we still don't really, I still always cringe a little bit when they talk about resting state correlation and they call it connectivity, because it's actually, we still don't understand connectivity and all the things that could vary the correlation. So for instance, as one example, you might have two areas that are fluctuating along, they have a certain correlation, but then you might have suddenly another set of neurons in that set of voxels that introduces another signal. That will make it look, if you average those signals together, it'll make it look like the connectivity has gone down, when in fact it hasn't changed at all for those neurons that are actually connected. So, and there's other things too. If you just increase the amplitude of one of the signals, they might be equally connected, just one happened to be going up a little bit more. They could, and that would increase the connectivity if you're against a noise floor. So there's all kinds of things like that we're not really sure we're looking at connectivity. And so if you're modulating connectivity, you could be modulating it in about 10 different ways that don't have anything to do with connectivity, or if you're modulating correlation. So that's still something that we're working with, that the field is dealing with. And my feeling is this: it's almost like the hemodynamic response was before, is that I think a lot of people are just kind of ignoring it and just calling it connectivity, and that will catch up with us later. But hopefully there are people trying to figure that out a little bit more carefully. We still don't understand what resting state signal really is there for, if it's there for anything. 0.1 hertz, it's slow. It's not just an alias hemodynamic response. There's actually 0.1 hertz neural connections as well. So it's still not clear why there's this resting state signal. Is it just spontaneous firing, or is there some truly resting connectivity that's going on? We don't know that. So that's a wide open neuroscientific question. Shimming is still an issue. So this is an example of how we have not benefited from vendors, because as far as clinical imaging is concerned, shimming solved. They have higher shims for most of their clinical images because they're so high resolution. The shim doesn't have to be that good. The signal dropout doesn't really happen. But at low resolution with EPI, shimming's still an issue. You still have signal dropout, especially at 7 Tesla. Around the base of the brain. So, and that's something that can be solved if you have the right shim coil configurations, but it just hasn't been. And until there's a large enough need, then it will be. So, of course, DBDT is still an issue. So how quickly you switch your gradients. So people are coming out with higher slew rates, but we can't really use these higher slew rates as much because we get peripheral nerve stimulation. We might be able to get around this with local head gradient coils. Again, going back to local head gradient coils because they have a smaller pivot axis that doesn't affect the rest of the body, so it doesn't flux as much through the body. So you can maybe go to higher speeds with that. Who knows? There might be ways of possibly getting around that. Maybe there's certain sweet spots in DBDT that don't cause peripheral nerve stimulation. We haven't really fully tested that whole range, but it's still an interesting ongoing area. Okay, so where do I think maybe the field is going as far as that's concerned? And I'm biased, of course. I have my own view, but if you had someone else up here, I'm sure they'd come up with very different ideas. So I think as we start to get a handle on individual variability and get a handle on methods for comparing individuals, we'll start to have more of a clinical impact. I think that, there's been a few preliminary papers out saying, oh, there's differences in individuals, and they seem to correlate somewhat with these traits. So that's just at the very beginning of trying to make a clinical impact, because that's ultimately what you have to do. You have to be able to put an individual in a scanner and make an assessment about that individual. And so you need a database to compare that with. Hopefully, you probably will need some sophisticated algorithms for pulling out this multivariate data, but then start to make statements about individuals. So that will happen, and as that happens, we'll have a higher clinical impact, which is really the bottom line for a lot of these things. Of course, we want to understand the brain better, but a big aspect of what's driving pretty much all the funding, almost all the funding in fMRI is if it's going to help people eventually. So increased vendor attention will happen with the clinical impact, and then we'll start getting many more products that are more fMRI focused. So more detail, and we might even get qualitative jumps in what we can do as we start to explore more column layer pattern effect mapping as they relate to columns and layers, looking at connectivity or correlation. I even make the same mistake. I call it connectivity, but still connectivity and activation mapping. So what I mean by that is that what's waiting for us, let's say we're all starting to do super high resolution imaging. We can start to look at connectivity across columns in resting state or activation. The connectivity across layers gives you a potential new dimension of looking at feedback and feed forward inputs based on which layer you're at in terms of where the activation is. Renzo Huber talked about that. So that's just beginning. And I think people are going to move into this a lot more. It opens up fMRI from blobology to actually starting to have detailed maps of inputs and outputs that can then be informed by more computational models. I still like to think that we'll understand the noise better. And so once we better understand the noise, once we can better characterize the noise on a time series basis and get rid of it, then our signal to noise will go through the roof in terms of our temporal signal to noise. So that's a huge aspect. I mean, solving this is much better than going to high field or adding RF coils or things like that. If you can really understand the noise and get rid of it, things will improve dramatically by factors of 10. So that's a big aspect. So computational models. So people are starting to make stabs at having fMRI data, having maybe DTI data, and making a sort of a rough computational model with nodes and edges, and trying to actually do some dynamic modeling and seeing if the fMRI data predict. So it's very early stages, and I think that will keep on going. That will do nothing but grow. In fact, I mean, just from my own experience with neuroimage, there's a growing number of editors who are computational modelers, and I think that and the reason for that is that there's more and more papers coming in that are sort of pushing things in that direction. And the basic idea is this, is that ultimately we're going to have computational models to understand our data. Right now, we can just point to blobs, or maybe 5 years ago, most of the time, we could just point to blobs and say, oh, that's occurring in the insula, and that's interesting, and then write it up. But at some point, the data are going to be so complex and so dynamic that you need a sophisticated computational model to then say, oh, well, this is this sort of interaction that might be explained by this sort of model in that regard. So it's no longer going to be sort of qualitative, but it's more going to be feeding into models. Okay, we'll keep on getting more insights into fMRI mechanisms through animal models and multimodal assessments. So even recently, Elizabeth Hillman and other people have been doing calcium imaging now, simultaneous fMRI and calcium imaging, looking at resting state, which is adding huge insight into timings and inhibition versus excitation and things like that. And also, a recent paper by David Leopold came out a few months ago talking about, looking at creating regressors from individual implants. And even if they're right next to each other, the hemodynamic response that correlates with that is extremely different all over the brain. So even next to each other, relatively close, you're getting all these networks that you wouldn't see otherwise just looking at blobs and taking the reference function there. Okay, so we'll keep on going. In fact, that might even grow as well. So another issue as well is, okay, so one of the issues in terms of looking at individual subjects is that you have to sort of put that individual subject brain into a way that you can compare it with other subjects. And sort of spatial normalization is still a challenge. You have many different parcellation schemes. Ultimately, you'd like to go beyond parcels and just keep the voxels and just sort of have perfectly registered brains where the parcels get smaller and smaller. Right now, we just choose the parcels, but we're, of course, getting a lot of partial volume averaging of many different choroidal tissues within those partials. So right now we're at a stage where we can maybe parcellate the brain pretty well and across multiple subjects and have a standardized parcellation. We'd like to actually get the parcels smaller and do more detailed comparisons. That will keep on going. That's just starting as well, I think. So this is my own bias, since I'm sort of pushing this myself, is we'll have an increase in, I think, so people have they've done task, they've done resting state, they've done continuous tasks, but I think that the way the field, I really do feel the ways, and I felt this years ago, but it never quite caught on, but I think more and more people are starting to think that maybe doing naturalistic tasks that are super well curated, so and exactly precisely timed, is the way to go. It seems like the optimal way to extract meaningful information from the brain, because you're sort of multiplexing all this stuff in there that you're keeping track of, and the brain is behaving in a way that's sort of evolutionarily natural in some regard. So it seems to make sense as a good match between what a subject naturally does best, keeps their attention, and in terms of an information extraction rate or optimization sort of problem. So that will keep on going. I think that will grow as well. And there's many different ways of analyzing this naturalistic task data. You can do cross-subject correlations. You could decode the task as well as possible based on regressors that you create according to what elements in the task exist. Or you could do encoding as well. I mean, there's different ways of going about this. Okay, real-time fMRI neurofeedback is another aspect that I think will keep on growing. It's one of those things also that has been around since the beginning. People haven't really done it because they didn't really know what to do with it. There were some false starts that occurred maybe in the early 2000s, but I think now it's starting to grow again. And yeah, I think there's some real substantial results that result in real therapeutic changes that occur much more effectively when someone is actually looking at their brain function as opposed to their autonomic nervous system response for feedback, as has been the case. Okay, like I mentioned, there might be a reintroduction of local grading coils. I'm personally pushing to get a local grading coil in one of our scanners, just because it might allow one to, first of all, I think they're more stable. And secondly, you can go to higher slew rates, higher speeds, less of a duty cycle issue. They never get hot if they're more efficiently cooled. And you can almost, it's not quite as powerful as our connectome, as the MGH's connectome grading coil, but you can sure go fast with it though. And because it's smaller, you can actually reach higher gradient strengths as well more efficiently. So I think that might come about. You might have an increase now. I think that now more of the field is catching on with embedded contrast or fingerprinting sequences. So once again, this is another example of how the field itself, so ever since the very beginning as well, we've been able to simultaneously look at flow, bold, and multi-echo and volume. But it's just that vendors have not really cared about these sequences that much because it's not a clinical sequence, so they haven't caught on. But it's a beautiful sequence. You can actually collect all this physiologic information simultaneously to extract metabolic information. Things like that. Another idea is sort of, embedding different types of contrast in the time series. So that's, I think, will come about, but once again, it has to maybe get more interest from vendors so that they can be distributed more. Vendors care about fingerprinting because it's sort of a technique that can be applied to structural imaging, which more effectively. So it saves time for the clinician. I think now we're getting kind of an explosion. We're at the very beginnings of an explosion in deep learning in all things, MRI and fMRI. And it lends itself perfectly to these huge multidimensional data sets. I think a danger potentially, though, is extracting these dimensions of information, but then you still have to make sense of them too. But I still think deep learning is a wonderful exploratory tool that then, so there's always a flip side. It settles in on an answer, and you always like to then know how or what it actually used to come up with these answers. And so it's important to keep that transparent for it to be truly effective. There's a growth in neuromodulation as well. There's better ways of putting neuromodulation devices in the scanner. People are becoming more comfortable with that. So that will come about too. And we're always looking for ways of modulating the brain, not only for therapy, but for activation, for all kinds of things. So that will catch on in general, and I think that to the extent that it's used in fMRI will increase. I think there'll be an increase in longitudinal databases for predictive biomarker discovery. The only database I know of right now is the UK Biobank that does this. So they're planning on scanning people for years, and then after the fact, seeing, who got Alzheimer's, who got schizophrenia, who developed this or that, and then they look back. Then they're going to go back to before they had it to try to predict. And it would be great to create a database like that also at the NIH. We're trying to get it started since we can have a very stable platform for doing longitudinal studies. Okay, RF coils, I think there'll be some growth in that. More elements, they'll be smaller. They might even be embedded in some regard. There's still a lot of room for RF technology to improve. I think we should, I don't know if we will, but we should do a lot of we have a lot of old data. And I think that the analysis methods have so improved that it might be worthwhile to go back and just reanalyze a lot of our old data since there's so much of it. And as scanning still becomes expensive, this is something you can do almost for free. So, as I mentioned before, a lot of so the industry MRI that does clinical scanning is still coming up with a lot of really, really cool things. For instance, things like compressed sensing. They actually are applying deep learning to image reconstruction. Instead of doing a standard Fourier transform, they just apply a deep learning algorithm to the raw data to figure out how to make it into an image. So here's an example of how that's both good and dangerous. In a sense, it's great for imaging, but let's say, and it works, but nobody knows exactly what it did to create. It's no longer a 2D Fourier transform. It did something, some transformation to make the image that's very robust to noise. But it would be nice, it's still important to know then what it did. So it'd be nice to do deep learning, but then keep it transparent in terms of what it finally used to figure out what it did. Fingerprinting is another example that could permeate into fMRI, where you embed a lot of different contrasts all at once, and then you pull it out after the fact. Okay, so what are the ultimate fMRI limits? So I think we can do whole brain submillimeter functional MRI pretty regularly. I think that we can collect simultaneous contrast, flow, bold, volume, and also multi-echo. I think that if that's standard, that would be an ultimate limit without really compromising much in TR. And that information is useful in the sense that, for instance, volume might be sensitive to capillaries. The ratio of flow to bold gives you metabolic rate. There's all kinds of things that sort of speak to neurovascular coupling that are advantageous by collecting multiple contrasts. Hemodynamic latency, I think, is able to be effectively calibrated. So I think that we'll have a method for either using a resting state scan to basically robustly make a latency map. So a latency map is roughly correspondent already to a blood volume map. So the larger vessels are usually longer latency, but not always. So if you can do that, then you can start to pull apart, delays down to 100 milliseconds with fMRI pretty robustly, if you are able to get rid of that intrinsic spread in the hemodynamic response. So motion and breathing is also solvable, I think. We can, either characterize the end-tidal CO2 in some way by maybe making a measure of what the depth of breathing is. There's a lot of room to model this effectively. A big problem also has been cross-vendor scanner and upgrade calibration. So people are throwing their data into data sets from different vendors and scanners and upgrades, and we're worried that the data have too much variability. And not only that, people who are doing studies on one scanner, they don't want to touch the scanner until they finish their study so that they can go on to another scanner or an upgrade. So that I think is solvable. I think either by making the standards more standard, having some certain standards for how they should be, or just coming up with better calibration factors. It's a very straightforward problem, I think. Registration. So this is, once again, back to the parcellation problem, but this is taken to a level of layers and columns. I think the ultimate limit would be how do you register brains across layers and columns? Well, first of all, that's almost impossible. It's like registering your fingerprints to other fingerprints. At some point, you can register hands pretty well, but you can't, it's maybe an impossible problem to then register fingerprints. So you can actually compare fingerprints in detail. So how do you do that at the level where things get really interesting at layers and columns? And if we're able to image those robustly, we can no longer do multi-subject averaging in this way, in the same way we have been, if we're going to be looking at this resolution. So that's, I think, will be solved as well. I think that, there's nonlinear, functionally related hyperalignment transformations that we can apply. So as I mentioned, detailed cross-subject functional registration will be much more common. Mostly not to do cross-subject averaging, but to do cross-subject individual comparisons. There's a difference there, and the latter is more demanding in terms of getting it right. Shimming is solvable. It's already solvable. There are ways of making the field completely homogeneous. If you have enough RF coils, if you have the right shim elements, if you understand the head shape enough, you can completely shim any image, echoplanar, even at 7 Tesla. The theoretical ability is there. It's just a matter of the technology sort of being applied to it. And right now, it's almost at the state where people think, oh, it's good enough. And so there's not much effort being put into it. So quantitative baseline fMRI, sort of extracting baseline metabolic imaging, I think is something that will be an ultimate limit as well. You might be able to get CMRO2. You might be able to get even other metabolites as well. CMRO2 is more of a low bar. That will be an ultimate limit in terms of what you can do there. One other ultimate limit, one other thing that I think will be common, and so the way I differentiated this is that these are, what I mentioned as where things are going, that's sort of the short-term ultimate limits are sort of like my long-term projections. So I think that, we've talked about this with my postdocs about deriving, I think one way of where a clinical inroad will happen in fMRI is coming up with the equivalent of a cardiac stress test. So a cardiac stress test is where you put someone on a treadmill, and the only way to see the disorder of the heart is to stress the subject a little bit, then they inject a contrast agent, and it shows up where it wouldn't show up if they were just sitting there. This is an example. I think that maybe a lot of resting state signal may not reveal much, but if you actually give them some sort of a naturalistic sort of movie that might contain, it might be a litmus test of some sort. It might contain elements that will stratify responses based on your psychological profile or even neurologic profile that you're just viewing or maybe interacting with. And that will become a standardized stress test that you can maybe apply clinically. Okay. I think processing platforms are still in the stage of growing. So, or it's like this Cambrian explosion of processing platforms and methods and approaches, I think eventually they're going to start to funnel back, at least in some aspect they have to, also to be used clinically. I think that there's going to be more standardization of the pipelines. You don't want to do that too soon because you sort of stifle creativity. As a matter of fact, I was reviewing a grant proposal that suggested that you have one center that has a standard processing pipeline, and that's it, and it's locked in. And I thought, in some sense, that's sort of advantageous for some people, but in other ways, it's a bad idea because it really does stifle the field. So there's a balance. Real-time fMRI ultimately, I think, will be used for therapy, some types of therapeutic responses. I think silent fMRI is doable. There are sequences even now that are pretty quiet. They're just lower signal to noise and a little bit slower. I think a combination of some aspects of the sequence, you might be able to even reduce the decibel level by 30 decibels by just maybe changing the gradient profiles just a little bit with echoplanar. Nobody's really played with this that much. So I also think noise cancellation technology will improve, and so you might be able to reduce the noise on both ends. And once again, there's not much work in this because it's not really a big deal. Everyone sort of tolerates it, but it can be done. I think that we're going to have to pretty soon go cryogen-free. A couple years ago, there was a helium scare. There's a shortage of helium, and everyone thought all MR was going to stop. And now I think they've just found another helium reserve, so which is good because you need the helium to supercool the magnets. But now I think that already at 3 Tesla, they have practically cryogen-free scanners. So that will be the future. It'll be cryogen-free. Although the problem is, if you have cryogen-free scanners, is that you have to have a whole bunch of power backups, because here, for these scanners, if the power goes out, it's no big deal. We have enough helium, keeps things cool. But if there's no helium there, if you have no active cooling, then they'll warm up and quench. So you need a power backup for that. I think databases will keep on growing. Right now we have big healthy volunteer databases. We have ADNI, we have other different disorders. This will keep on growing. It'll grow not only across disease, but it'll grow across modality. And I think truly to generate biomarkers, you have to compare different shades of diseases and differentiate, not just saying, oh, they have this disease or not. So you need these bigger databases of these the various diseases. NIH also is a great place to doing that. So hopefully we're going in that direction. More longitudinal databases, because one of the aspects of doing fMRI or doing imaging at all, or any sort of clinical diagnosis is, you'd love to have better predictors, either genetic or imaging-based predictors. And so the only way to get those predictors is to be able to image the brain before the disorder happened. And so that's why you need these longitudinal databases. At least on the imaging side, you need to do that. So I think naturalistic paradigms will be all over the place in the long run. And I also think, I may have mentioned this later, but I also think that naturalistic databases, creating a well-curated naturalistic stimuli, and have a database, and maybe have the country or the world agree on a certain set of naturalistic paradigms, it'd be interesting to create a database of that data. Because I think there is much more power in naturalistic databases than resting state. Just have to have everyone agree on what to do. So that would be kind of a really cool thing to try. And not only cool, but I think useful, very useful. I think that, deep learning approaches versus standard processing, I think deep learning will continue to grow, but I actually think that there might be a tension with this, because deep learning is so powerful, but once again, it becomes a black box in some regard. And there's a whole school of people doing processing that sort of don't like black box approaches at any level. So I think that will be solved by having deep learning methods somehow report on what they've done more. And it's easily possible, I'm sure. So anyway, okay. I don't know much about deep learning, but that's just what I sense from talking to people. Other contrasts. So, neural current contrast has sort of always been in the side. Metabolic rate contrast is definitely much more established for looking at changes in metabolic rate, less for baseline. A new type of contrast that just came out that was very preliminary data at ISMRM this year was looking at elastography changes. And they suspect that the elastography changes were neuronal in origin as opposed to just hemodynamic. So that was kind of interesting. pH might be a contrast mechanism, diffusion. They're all MR sensitive to all of them. And once again, I think the resting state will be figured out completely within the next 10 years or something like that. Or almost completely, much more than we understand it now. And it will therefore be a lot more useful too. So I think this problem will be solved too. I think we'll solve the physiologic fluctuations problem. My gut's feelings tells me it's solvable. And so the only limit then will be thermal noise. And then if the limit's thermal noise, we can easily have images, like I said, of signal to noise of 1,000 to 1 at 7 Tesla. And so if that's possible, you have time series where the signal to noise is 1,000 to 1. So it really is a big deal to get rid of all the rest of that physiologic fluctuations. And it's a much harder problem than we think. Then we've tried, and it's many possible solutions, and it hasn't worked yet. Also, correlation as this problem that I've been having with correlation as it relates to connectivity will be first recognized as a bigger issue. I think people are kind of ignoring it in the field right now, but I think it needs to be brought out that just seeing correlation changes does not mean it's necessarily a connectivity change. It's interesting, but it's not a connectivity change as one defines connectivity. Okay, so what could change? This is almost the last slide, but so what could change everything? So all these things are sort of all where you take what you know and you sort of just project. And that's fun to do, and it gets completely inaccurate over 10 years. And it's not that it's kind of interesting. It's sort of fun to think about as an exercise, but there are things that could change everything. Like for instance, if someone came along and discovered room temperature superconductors, if you could do that, then we can start wearing our scanners on our heads. Then we don't need the big dewars of coolant to hold it. So that would completely change the face of MRI and fMRI if we could do that. It'd be a wonderful thing. A new robust direct neuronal contrast mechanism is discovered. That would change everything as well. We'd all jump into that direction probably. And this is important. I think this is actually what the field is waiting for. So one powerful and unique clinical application of fMRI. So something that is like a killer application that no other clinical techniques could do, and that really saves money and time and helps patients. So if that comes about, then all of fMRI method development will be accelerated. Things will improve quickly because then suddenly you have the collective manpower of all the vendors sort of working on this, making it better. And then things will cascade from there. But we just need one to start. And we don't have one. We have a few sort of things, but that's it. So any proof that MRI is either therapeutic or dangerous would MRI in itself, not imaging or fMRI, so just the magnetic field or the RF pulses. If they suddenly showed, it really improves lifespan by 10 years, then there'll be scanners all over the place. On the other hand, I always worry. Every once in a while, I review a paper where some study is showing that you put a person in a scanner and their EEG gets different, or somehow it might cause long-term something. Who knows? But they're all sort of usually proven to be wrong. I mean, there's one study that came out recently that claimed that it was a cardiac one that claimed that MRI somehow changed your genetic structure. You had more likelihood for mutations or something like that. So that also was sort of over time quashed as well. So, but these things could really flip things one way or the other if they come out. And I think MRI, luckily, has been around long enough that if there were any problems, we'd see them by now. So that's at least a good thing. So if we can actually show definitively that layer-dependent fMRI can robustly get at true neural causality, that opens up the power of what fMRI can do to neuroscience. So there's a much larger neuroscience community that this is all they care about. And they don't like fMRI because it just kind of shows activation stuff here and there. It doesn't actually get at causality and connectivity, and we're sort of suggesting that we can get out of that. But if we could actually do this with layer-dependent fMRI, then that would be a breakthrough in how fMRI is used by researchers. You'd have hardcore neuroscientists much more embracing it, and neuromodelers as well. So there's other contrast agents that are sort of, people are working on this, that are sort of in the background, like labeled agents or nanoparticles for either picking up neural currents, or if you could label them with all kinds of things, not just things that stay in the blood. You could have labeled them to dopamine. You could label them to other sort of neurotransmitters or whatever. Right now, the sensitivity is too low because they rely on susceptibility contrast. But if there's other types of MR agents, MR visible things you could stick them to, then that would be a huge improvement. And I guess one of the people working on this the most is Alan Koretsky, so he might be worth talking to. Okay, so second to last slide. I just like to re-emphasize, though, that none of these things sort of is developed in a void. It's all pretty much, these are the pillars that drive fMRI. So there's the basic technology, there's the methodology, which is processing, paradigm design, everything like that. There's the interpretation of the signal that all feeds off this. And then there's finally the applications. And I think that the more I thought about this diagram, I've been staring at this for years, but really the methodology, technology, and interpretation sort of triad is, they work together really well. And I think the bottleneck is actually in the applications, where the problem is that it's easy to develop a methodology and say on a few subjects, oh, here, look, this works better, or technology that everyone just tries. But it's much harder to say, oh, this actually works for doing this thing, or helping this patient, or doing whatever. Yeah, there's so much variability in individuals and in the noise and all kinds of things that you have to do many studies to show these sort of things actually work. And so I think there's limited money and time. And so there's really a bottleneck of how the methodology is being optimally applied to the application. So I think more people to work on sort of, fostering the methodology to try to use it and test it and work out all the issues, I think is needed to increase the applications. So then I'd like to thank you. Also, I'd like to thank all the attendees who came to all 40 lectures. I don't know if anyone came to all 41 of them, but and of course the speakers, because they offered to share not only the video of their talk, but PDFs themselves or some version of it. And then of course Rock Mikado, who's always appeared. He's sitting there in the back. He's gotten this whole thing going. He's coordinated everything. He puts them on the website. If you have any issues, you talk to Rock. As far as that's concerned as well, but he handles them. And then, of course, Dorian as well for handling a lot of the announcements and the scheduling as well. So, all right, thanks. And if you have any suggestions for the format of the talk or whatever, just talk to me or email me as well. So, all right. Okay, good. Well, have a good winter, fall and spring.